This video goes a bit deeper into ligand bonding with metals. The reactivity of a ligand reacting with a metal is simply called Ligand Association. As described in the orbital picture below, this is another example of Lewis acid plus Lewis base. Lewis acid accepting electrons from a Lewis base which donates electrons. This is shown for tetrakis triphenylphosphine palladium. The ligand metal bonds are generally much weaker than the covalent bonds that you have studied this year, between carbon-carbon atoms or carbon-hydrogen atoms, for example, which are on the order of 400 kilojoules per mole. For these much weaker bonds, ligand association is in equilibrium with the ligand dissociation reaction, the microscopic reverse reaction. Tetrakis triphenylphosphine palladium is stable in the solid state, but in dilute solution, triphenylphosphine dissociates from the palladium metal, and the overall solution is a mixture of tetrakis triphenylphosphine palladium, tris triphenylphosphine palladium, and bis triphenylphosphine palladium. In class, we'll discuss what is the total valence electron count for the tris triphenylphosphine palladium and bis triphenylphosphine palladium. And we'll discuss the significance of the valence electron counts. We'll now scroll down the page and describe what happens with other ligands, specifically alkenes and carbon monoxide. The bonding picture of alkenes with Lewis acids, which have filled d orbitals, is more complicated than what we have previously seen. There is electron donation from the highest occupied molecular orbital of the ligand with an empty orbital on the metal. And there is also electron donation from a filled d orbital of the metal with the lowest unoccupied molecular orbital of the alkene. This slightly strengthens the metal-ligand coordination in a phenomenon which is known as back bonding. So there are actually 2 electron pairs, or 4 electrons in total, that are involved with metal-alkene bonding. But since this involves orbitals that are lower in the periodic table and larger in size, each of these bonding associations is much weaker than what we see for covalent bonds. In my opinion, we do not have a good way for describing the combination of bonding and back bonding, and so we typically simply show a line describing the interaction of the metal with the alkene as a pi complex. But I'll point out that for back bonding, the orbital symmetry of the d orbital correlates with the orbital symmetry of the pi star, or alkene antibonding orbital. The other example of back bonding presented in this course involves bonding of metal with the carbon monoxide ligand. In this case, carbon monoxide donates a pair of electrons to an empty orbital on the metal, but then there is also the back bonding, or the donation of electrons from a filled d orbital with one of the atoms involving the pi star or carbonyl antibonding orbital. Carbon monoxide in the all-octet fulfilled resonance form has a bond order of 3. But due to back bonding, the donation of electrons to the antibonding carbonyl orbital, this diminishes the bond order of the carbonyl ligand and weakens the bond strength of carbon monoxide. Think about how infrared spectroscopy might correlate with the bond order of carbonyl ligands. And if we have time in the class meeting, we'll spend a few minutes talking about this. I'll show the molecular orbitals of carbon monoxide. This is the structure of carbon monoxide. Carbon is the gray atom, oxygen is the red atom. The lowest orbital provided by Spartan is a sigma bonding orbital. It does have some lone pair character on oxygen. This is a sigma star antibonding orbital. These orbitals are pi orbitals. Consistent with the triple bond, there are 2 pi orbitals 90 degrees to each other. The highest occupied molecular orbital has substantial lone pair character on carbon, and then the LUMO orbitals have pi antibonding character with larger lobes on carbon. Turning to the last page of the worksheet, this is the structure of chromium hexacarbonyl. The geometry is octahedral. In the class meeting, we will discuss what is the formal oxidation state of chromium, how many d electrons come from chromium, what is the total valence electron count, which atomic orbitals of chromium are accepting the electrons from the carbonyl ligands, and which atomic orbitals of chromium donate electrons to the empty pi star orbitals of the carbonyl ligands. This will provide a picture of bonding and back bonding, and we'll conclude by discussing what might be the bond order of the carbonyl ligands. To conclude this video, I will show a Spartan picture of the octahedral chromium hexacarbonyl structure. This is the chromium hexacarbonyl structure, and I tumble it so you can see it in 3 dimensions. This concludes the video on ligand bonding.